صح أن هذه كنا تحريا
Can anyone hear me?
Yes, Daniel, we can hear you.
Great. We have about 2 minutes left. Is it streaming on YouTube now, Lego?
Oh yes, I've started streaming on YouTube as well.
Okay, that's fine. Wait for 2 minutes and then we'll start.
Okay, perfect.
Okay, it's time. All right. Good morning, everybody. I hope my voice is coming out clearly. Welcome again to week 5 of the Breaks Idea Data Analytics program. I know it has been a long stretch. New things to learn, new topics every week, coupled with learning a new language. I'm sure it's many of you are going through it. I know it's not easy, but then it's one of those hard things we have to do over, learning a programming language and at the same time combining it with a topic peculiar as astronomy. So my name is Daniel Ebo. Today, this morning, I'll be sitting in for Ronaldo, and then we'll be talking about time series analysis. Last week, we had the topic on astronomical data sources, where JAM took their time to take you through different types of astronomy sources, data sources in astronomy, images, catalog, and spectroscopy, and the rest of them. And today is just more like an in-depth into one of those kind of data sources. So let's get started. Yeah, so what is time series? Like I said before, we're just going to go in-depth into one of the topics that was discussed last week. Time series is nothing other than it's a kind of study that deals with analyzing information related to data, right? Many of you did things like economics or statistics. Oftentimes, what you hear is something like you are comparing the prices of goods in the market, or prices of commodities, prices of currency, daily, could be weekly, could be monthly, it could be yearly. So time series has to do when you are trying to analyze the variation of a measurement over time, right? A good number could be, another thing is, for example, those in atmospheric physics or environmental sciences, something like temperature during the day. See, temperature can vary in the morning. It's not exactly the same. The temperature yesterday might not be exactly the same temperature today. Same thing as wind speed, same thing as relative humidity and all that. So in astronomy, we take astronomical data sets, and a good number of them are usually like imaging, right? Now, when you do these observations are taken in time. And if you have the opportunity to continuously measure or take the subsequent observations in sequential form, like, one in 10 seconds ago, another 10 seconds in the future, and then you arrange all of these things, in that case, you are able to provide what we might refer to as time series data. Like I said last week, Priya was talking about, showed us the concept of CCD when she introduced the concept of imaging in astronomy. For photometry, we use CCD imaging system. A good example is the image you're seeing here. You can say this is a snapshot of the sky, and you can see that the image on the right is showing you a zoom into one of the objects. And then you see the line that is centered, the green line centered at the center of the star or whatever object this is, and you can see the brightness of the object. So this is a concept of imaging, right? So in astronomy, when you have a time on a telescope, and most especially optical telescope or infrared telescope, and you observe over time in different time scales. You take like time scales of an object. You can produce images like this multiple times. Let's say you did this 10 minutes ago, and then you take another one in another 1 minute. So you see, in 10 minutes, you are going to have, if you are supposing you are taking image snapshots every minute, it means that in 10 minutes, you will have 10 images. Now, in each of these 10 images, you will take the brightness or fluxes or magnitude. Now, in that case, when you do that, you'll be able to now have a data that represents measurements you have taken about the object at so time. And then you can stack them together, and then you can have what you might refer to as time series analysis. Now, the question will now be, why does it matter in astronomy? Why do we take time series data? For the same reason why we take time series data for different other fields or different other topics, both scientific and financial in the business world. It's for the same reason. You want to do what? You want to analyze the variations If in the case of finance, you will say, oh, you want to analyze the variation of trends in maybe if it's a currency or if it's a commodity, for example, something like fuel price. You notice now because of the Russia-Ukraine war, the prices of fuel have skyrocketed. So if you take the data from last year and compare it to this year, you see that, oh, this year the price of fuel have skyrocketed. The question will now be, what triggered the price of fuel rising than what it was last year? You can now relate it to geopolitics and say, oh, because US, Iran is going through a war. Now, in the case of astronomy, we also see trends where brightnesses can vary, and they vary for multiple reasons. Many of them have been listed here. In some cases, the stars could pulsate, right? So where you can either it contracts, or in some cases, you have a case where you have a binary system and one is shadowing the other. So maybe when it shadows, depending on the line of sight by which we are looking at the lights coming from the star, if one object comes and shadows it, the light might deepen, right? In some other cases, if they are in phase, both of them could actually just brighten more. So these are some of the things. These are some of the reasons why we do it. It is far more bigger than this. It can also be exoplanet. For example, imagine a star having a Jupiter mass, a planet having this similar size as that of Jupiter, which is quite massive. If you are looking towards the star and the planet transits to it, it's going to deepen the light of the star, just little deepening or darkening, right? So this is also the method for discovering exoplanets around stars, because you cannot detect exoplanet directly. These are the methods, indirect methods of detecting exoplanets. It could also be a case where black holes are creating matter. So if a black hole creates matter, right? You're looking through the black hole, it can brighten than what it used to be. It could be a case whereby there is a nova or supernova. A supernova is when a star explodes, a massive star, not like the size of our sun, but very super. I think about at least eight times the mass of our sun explodes. They can be very, very catastrophic, and it can be very, very bright in the sky. So in that case, you're going to see where the brightness of the star could jump. It can also be in the case of an AGN, right? Where maybe that's also accreting matter towards it. So things might also fall towards the AGN, and the brightness can vary. So there are multiple reasons. So these are different. There are so many different science use cases in astronomy when it comes to time series data, and it cuts across wavelengths. But anyway, we don't want to dwell on this that much because we want to get our hands dirty into looking at some of the data. But then, with the concept of time, is something that we're all familiar with. The reason why all of you are here this morning is because we agreed that we're going to meet by 7 a.m. GMT, which is a 9 a.m. South African time, right? So we already have the time that is known, and most times we call it GMT, same thing as UTC, right? Good. But that is for our own understanding. In astronomy, we also have different kinds of times that we use. These were mostly adopted in the early days of astronomy, and for many reasons, to be honest, many of them I'm not so familiar with them, but I'm just going to mention them, and then you also take your time to read through to understand maybe why they are useful today. We have what we call the Julian date. Julian date is what basically represents the count of dates for over a period of time. Like every day is represented as a time, as one. Every day is represented as one shot. That's what it is. Every day is represented as one. Well, the Julian date started counting for a very long time ago. We have the modifying Julian date, which specifically tells, I think, is it something before BC? I don't have that of it, but these are the common ones that we use today for timing. And these are described fully in the notebook in the in the exercise, in the learning exercise that is also accompanying this topic. So we have the barycentric Julian date. So these are the ones that are very peculiar for correcting for Earth's motion. It's just like it's a fraction of day. It's a small fraction of day because the center of the solar system of our own solar system is not Earth, right? This is towards the sun. So, but when the light is coming to us, you just need to take account for that differences because of the Earth motion. And then we have what we call the heliocentric Julian date that has to do with like you correcting to the solar reference frame. So you are correcting this light coming from the source to our sun's reference frame instead of that of Earth. So these are the few concepts I would like to talk about before we go in depth. The next thing is why do we do time series analysis? Like I said before, it's just for us to get information about how astronomy objects behave over time. Right? If you have an instrument and you point into the sky and you are following a particular object, the more you follow it, the more you take snapshots because there's something you are measuring. You are either measuring the flux. Most especially what you're going to do is to measure the flux, irrespective of the wavelength of the instrument, irrespective of the wavelength you are flowing it with or observing it with, you will continuously measure the fluxes. And when you measure the fluxes, you record them. And when you record them over time, it could be in a few hours. If you have the logistics, it could be in weeks, it could be in months, it could be in years. But when you measure them over time and then you plot them, you can now plot the flux against the time. And if you do that, you have what we call a light curve. So a light curve is simply other than the time series of measurements or brightness of a measurement over time. So usually plot the flux against the time. A good example is this figure here. This figure on the top right of this slide, you can see this is I think this is one of the variables that it was observed with Kepler. Kepler is one of those space telescopes that were originally used to search for exoplanets, and they do have the ID numbers for the number of stars that is observed. So usually presented at KIC something something. So in this case, you can see that this is the brightness of the star. Although I think there's also a bit of instrumental things here. I didn't make this plot, I picked this from literature, right? So you can see that this light curve, you can see there's a sort of variation. It starts dipping, and then over time, you see it go up again, and then it dips again and continuously stays in the same location, and then dips again and then goes up again, continuously like that. So these are the kind of things. You can see different variations on trends in light curve, right? Now, like I said before, how do you produce a light curve? If you point your telescope to the sky and you start taking snapshots over time, if it's an optical image, you follow this step whereby you observe repeatedly, and when you observe these things, you calibrate your data. Calibration is, I think, is part of what Priya discussed last week. You have the process of taking your image. You also take instrument biases. Or sometimes you take the bias like sky bias or flats, in the sky background, right? You want to also take information of the sky, which you call the flats, and that of the instrument itself. And then the reason why you do this is that you want to remove atmospheric information, the sky information from your image. You also want to remove the noise that might be coming from your instrument, so you need to account for it. So usually these are the steps you do during data reduction, but we are not talking about data reduction. Is not part of this course, but this is what the steps you need to take to be able to arrive at a scientifically ready data that you can use to do your analysis. So when you use regular small telescopes that you use during outreach, those data that you get are not directly ready for science, right? If you use a telescope and point to the sky, it does not mean that the image you are seeing from the GUI of your telescope, you don't just use that. You need to account for these corrections before you can have a science-ready data that you can use to produce a figure like this. If you read about Kepler telescope or TESS, which is the one that is still operating, you'll get you get a better understanding of the steps that the observatory team go through into producing a data like this. So like I said, we are always looking for variability, right? And variability can tell us a couple of things. It could tell us information about whether there is oscillations happening in the star, right? You know, when things can be dangling. It also tells us whether there is an eclipsing. In the case of an eclipsing, like I said before, binaries. If a binary is two stars are within a center of within a common center of mass, and they are moving within a common center of mass. If you are looking at it far away, there comes a time where one could blur the other, right? Or shadow the other. In that case, you could see some dips, like the brightness might dip in a bit and all that. I've talked about exoplanets. I've also talked about AGN. So this is a huge field. There are people in astronomy that the only thing they do is to look at study flare stars, some study what we might call transient, like some exotic variable, very exotic variable sources that usually have this sort of sudden brightness and fades off and may not happen anytime soon or happens at regular intervals. Yeah. So and then like I said before, we do this. You study the light curve, you get the light curves. What can you do with it? There are different kind of analysis that you can do with it. So depending on the kind of science that you're interested in, light curve analysis could tell you information about the rotation period. A good example is in astronomy, one of the common ways of measuring the rotation period of an object is through light curve analysis. With light curve analysis, you can take the light curve data and then you perform a period analysis on it. And with that period analysis, you'll be able to create a phase to see how truly the oscillation of the light curve of the star is and how it happens in phase, right? It gives you room for opportunity to study things like flaring. If a star is flaring, for example, our sun is a G-type star. It flares. When the sun flares, what happens is that in the atmosphere, a portion of the layers, the materials are burst into the air, get injected into the atmosphere, right? So if you're looking at it, you see sort of a burst of matter leaving the surface of the sun. And what happens is that you see that portion of it, you see a bit of brightening. The light will brighten over a short period because these things are not constant. They happen at intervals. So you can take note of that. And studying the flare gives you room to understand, okay, how frequently does it flare? When it flares, what is the duration of the flaring, right? And all that. And how bright can this flare be? And the rest of them. And it also tells us information about magnetic activity, because for most of the objects, when they start flaring, you have things like coronal mass ejection. You know that, oh, there's a bit of serious magnetic activity happening within the layers of the star, maybe in some cases coming from the chromosphere to the, maybe from the photosphere to the chromosphere to the corona and the rest of them. There's always like magnetic activity that is driving energy upwards towards the stellar atmosphere and the rest of them. For those who are interested in exoplanets, the light curve is essentially one of the best parameters that you can use to study exoplanets. if you have data of, if you have light curve, if you, for example, you have access to telescope data where you have had constant observation of light curve, you can analyze it and begin to find dips or transits where maybe the planet is blurring the light of the star. So there are many things that you can do. In transient astronomy, like I said before, you have a case of supernovae. You also have things like, I think, CVs, cataclysmic variables, where in the case of binary systems like a white dwarf and a low mass star, there's always like this sort of strong mass transfer going on between them that can always give off this sort of outbursts in the light curve. Some of them can be periodic, some might also not be periodic. And this light curve study can happen across the electromagnetic wavelength. It is not restricted to optical, although most of our analysis and things we're going to look at today will focus more on the optical side. But I think there are a few examples on X-ray and radio. So you see that this is done across the electromagnetic spectrum and can be used to study different kind of objects, both for stars and for galaxies or any other things you can think of. So yeah, and like I said before, if you looking at this picture, you have a light curve. What can you do with this light curve? You can use this light curve to perform period analysis. It will be like the period analysis tells you how long orbital you can use it to measure the either orbital period or rotation period. It means, okay, how long does it take this star to rotate around its axis, or how long it takes for it to move around its orbit. There are so many stars that usually have like very short rotation periods. So this gives them for one to study and get the understanding. Then another thing one can do is using the period analysis, you can use that to fold your light curve to see the rotation phase over time. So, but one of the common methods for doing this is what you might refer to as for period analysis. I think there are a couple of methods, but they usually follow, it's a Fourier transform methodology. You know, Fourier transform allows you to gives you the idea of how objects can move over time. So you have the sine. Some of you have done things like sine waves, you know, or cos and the rest of them. So you have different methods, but in astronomy, there are some of the Fourier methods that have been revised for doing period analysis. Popular among them is what you call the Lumsky-Argo periodogram, which is the one I have used. There are many other methods, but like I said, this is just an introductory course for us to get started. So what this does is that the Fourier transform allows you to analyze the series of data that you have, time series data, and find the optimal period that can be used to describe either the rotation or the orbital period of the star. And in that case, if you obtain that, you can now use it to phase fold the light curve. In that case, you can be able to now produce a phase like this, where you see, oh, how you see this is a sign. This is a sinusoidal wave, right? You could tell you could see how it's going from the trough to the other one of it. So anyway, and then it allows you to also plot it in frequency. But we're going to just do that now if we go to the notebook. Another thing I want to touch is that for this exercise, we are going to look at TESS data. So TESS is called Transiting Exoplanet Survey Satellite. It is one of NASA's mission to obtain astronomical light curve. It was a replacement to Kepler. I think Kepler was launched in the early 2000s, and after a few years, Tesla was also launched. to continue on where Kepler stopped. And majority of the goal or objective of TESS is to help provide enough data to understand stellar variability, because we have different kind of stars. And because we have different kind of stars, they usually show the variability are different. So you cannot use one variability method to describe all stars. You have different variability to describe stars. This is also very essential for finding exoplanets. In short, thanks to Kepler and TESS, the astronomers' understanding of exoplanets today, the growth that have been observed or obtained with exoplanets today. So, sorry, exoplanets are planets that are not in our solar system. So exoplanets are planets revolving around stars. In the solar system, we refer to them as planets, but outside of our solar system, planets evolving or orbiting other stars are referred to as exoplanets, for those who do not know, like those who are new to astronomy. Yeah, so we don't, for some reasons, because of our own limitations, you cannot see an exoplanet with your eyes. You can barely see a few planets with your eyes in our solar system. So you cannot see exoplanets with your eyes. So what you can see is a star. And as we have telescopes or with telescopes, you still cannot, it's still very difficult to point to exoplanets, because again, they are very faint, although there are numerous of them in solar system, different solar systems, but because they are very, very faint, you're not able to see them. So, but then there's been a couple of method by which you can use indirect method to find these exoplanets. And one of those, the method is called transiting method. And TESS have been very, very instrumental in finding this exoplanet, because with TESS light curves, you can easily, and in analyzing the light curve, you can easily see such dips, transit dips that is happening as a result of exoplanets dimming the lights coming from a star, while TESS was observing the star or picking the lights coming from the star. So TESS is useful for many reasons. It has short cadence and then of 20 seconds. So imagine within 20 seconds, you already have a snapshot. In another 20 seconds, you have a snapshot. So imagine if you point to a star for like up to, say, 10 minutes or 1 hour or 2 hours, you will have a good number of data points that you can use to perform light curve analysis. And again, depending on the region of the sky, TESS usually does continuous observation, like you call it sectors, where in different sectors, it tries to map the sky, and he will take this data, and then maybe for another few months, it comes back again in another sector, and it observes the same portion of case. You can see you have enough data, although most times there can be a lot of gap in this data, which is where the Lomsky becomes very, very ideal for doing the period analysis. So in the course of the science program, the team developed a package called LightCurve. It's a Python package for analyzing, querying. It's a LightCurve. It's a package, a Python package for querying TESS data. It allows you to query TESS data. It allows you to get the target image, what you call target pixel file. Allows you to query the light curve itself. That's the flux and time data. And then you can take that data, you can save it on your PC, you can analyze it, you can do anything that you want to do with it. So it is one of the easiest way to get data. I'm not sure if it was mentioned in the data sources last week, but I think has been highlighted somewhere before. But anyway, so that is it. And I'm going to stop here, but we're not going to, if you have any questions, you're going to put it in the chat, and then I'll take a look at them. But remember, this course has more to do with hands-on, right? So, okay, I see a question. How is the flux related to the brightness of the star? Also, what are the units used for flux and brightness measurements respectively? Thank you very much, some predate. So yes, so in astronomy, each time you point your telescope, you are measuring something. You are measuring the fluxes. So the fluxes are what we call apparent fluxes because this is dependent on a number of reasons on the instrument. Like I said, there are so many things that you have to account for. In the case of optical, we have different when Priya was talking last week, there was a conversation around magnitudes, right? Magnitude is the logarithmic way by which astronomers in during the ages devised to describe how bright an object is. But then magnitude can also be converted to flux. So you have type of magnitude. You have the apparent magnitude, and then you have the absolute magnitude. So absolute magnitude tells you, okay, if you know that this star is supposedly 10 parsec away, how bright will it be at 10 parsec away, which has become like the reference frame. Because remember, these objects are in different parts of the sky. Many of them are known. So if you happen to know the distance, right, you can quickly also calculate the apparent magnitude. So back to your questions, the fluxes are usually in Jansky. Yeah, the fluxes are usually in Jansky, be it in optical, be it in radio, or even in other wavelengths. Though in some cases you can have different conversion rates to it. Then for usually in optical, they like putting it in mag, so mag. But then you also need to account for the filter. So filter is like the range of the wavelength by which the telescope is observing in, because even when we say optical, it does not mean that it is not looking at the full optical wavelength. It's particularly looking at a particular wavelength range, which we usually refer to as filter. So depending on the side of the optical wavelength, it can be described as red or blue, right? So red, if it's tilting towards the infrared portion of the electromagnetic spectrum, you refer to it as red. If it's tilting towards if it's closer to the UV side of it, you refer to it as blue, right? Yeah. So so the MT there is magnitude. F stands for flux. This is just me just trying to describe it for you. The F there stands for flux, and the M there stands for magnitude. Okay, so is magnitude as a, sorry, I'm not sure what you mean by magnitude as a function of time. So that is actually the definition of light curve. So when you measure the magnitude at the time of observation, you also note down the time of observation. So in that case, you can relate the observation to it. Okay, what is the difference between light curve and time series? So I'm not sure what you mean by time series curve. So time series is just a general term that is used to deal with any kind of observation that has to do with time. Like I said, it is not peculiar to astronomy. It is cut across almost our field, be it in medicine, be it in healthcare, medicine, healthcare, be it in economics, finance, accounting, be it in environmental sciences, like remember weather, the weather data. You can see temperature, you can see rainfall. The short, each time if you go to Google now and start temperature, you're going to see a graph, even though it tells you the temperature for the place you're looking for, you're also going to see a shot of a graph that tells you, okay, maybe the time could be for hour, how the temperature could vary for the day or could vary for the week. Yeah, so also cadence is more like the intervals by which the observation happens, right? So if you say 10 seconds. So let's use for example 10 seconds. So if you're observing, if you're using like high resolution or fast photometric, doing something like fast photometric, your object can be very thin, but you say 10 seconds. So 10 seconds is like, okay, you configure the telescope, and in every 10 seconds, it takes a snapshot of the of your target. So you know that every 10 seconds it is taking a picture, right? Recording the image of the star you're observing, or AGN or galaxy that you're observing. right? But this is also dependent on the strength or resolution of the telescope, and also how bright the the target you're observing is. So if your star is very bright, you can even do something like, for example, at SAO, we have a telescope, the 1 meter or 2 meter telescope that has the instrument called SHOCK. So SHOCK is very, it's a very strong camera. So if your star is very bright, it can do things like 1 second cadence, where it can be taking snapshots in every second. But if it gets fainter, like maybe your star is very faint or it is very far away, so the magnitude is very faint. In that case, you can increase cadence to like 10 seconds, 20 seconds, so that you'll be able to have a good image. At least the star will be able to show in the field of view, and then you record it. So that is what the cadence is all about. How is phase folding performed in time series? I think we'll get into that in the notebook, because this has been described in the notebook. Transient events are not time series. Should time series always have to be periodic? Well, I wouldn't say so. So transient events are also time series. They are time series because how do you know that an object is changing over time? How do you know it is a transient? It's because you have been taking the data over time. Maybe you point to a particular portion of the sky to an object, the brightness stays the same, and then maybe after 1 hour, you see it jump up. You see the brightness jump up and continues going up, and maybe after another hour, it comes down. It is time series, because without the time, you wouldn't be able to differentiate the periods or the events, right? Yeah. So, and you said, should time series always have to be periodic? Not necessarily. Yeah, it could be. I'm not sure. Yeah, it doesn't have to be, because periodic is more like maybe when you have clear intervals. Some are non-periodic, but there are other things that you can also look for. It could be like, oh, there can be some sort of brightening. It does not mean that the brightening will happen at a particular interval again. In some cases, they are not periodic, right? In some other cases, they are periodic. Like it's really for things like some variables that some variable stars where that flares, or some stars that flare regularly. So you can say, oh, it's going to flare in the next. It flares regularly every 5 days, or oh, it goes into outburst every 2 years. For CVs, there are CVs that, oh, these stars, the objects, they go into outburst every 2 years. In that case, because it has been studied over time, you know that, okay, you know when to expect the variations happen. But I see Harrison's hands up. Harrison, can you ask your question, and we can move straight to the notebook?
Yeah, thank you, Daniel, for your wonderful presentation. Can you hear me?
Yes, I can hear you.
Yeah. So you talked about making analysis using light curve, and I think what I would say, the main reason I registered for this course is because I was so much interested in plasmas, as astronomy plasmas. So I don't know if you could say something about the hot plasmas. And secondly, is it possible for us to use the light curve to get data to analyze hot plasmas? And about the capstone projects, they said that it is expected from us to make our submission within 2 weeks. So I don't know, is it possible, if I want to work on hot plasmas, is it possible for me to make analysis within, let's say, in a week using time series analysis? I don't know if you understand my question.
So yeah, I do. So coming from the first one that has to do with plasma, I don't know if I should say light curves. It might be useful, but plasmas are, I think they are high energetic. So you should be looking at things like X-ray, gamma ray, for or UV for plasma study, but it's not something that I work on. But I think these are high energetics. So are you looking at it for in respect to stars or in respect to galaxies or AGN?
Yeah, I'm going to look at it in respect to stars or galaxies.
Yeah. I wouldn't want to make guesses for you. I'd rather say maybe you need to do more research on it, but I do think it's things that you do with high energy astrophysics. And in that case, a good place to start will be looking at X-rays. There are many X-ray telescopes, many of them, or majority of them, their data is open, but you will have to read the documentation to figure out how to analyze the data, how to query, how to obtain the data, how to clean the data, and also how to perform any kind of plasma physics that you may want to do. The only thing I can say a little about is maybe things that have to do with corona, like when in the case when you talk about coronal mass ejections, that is the ejection of plasma into the stellar atmosphere, right? But these are things that you can get within the X-ray, things like Rosetta, XMM Newton, they provide data around it, but I'm not sure if they provide time series data. I think if Rosetta might provide the time series data, but it also depends. It's not, I don't work, or it's not something that I've worked on, right? I know some people usually write proposals to write proposals to use the telescope to get such data. But again, any topic you're going to work on, make sure it's something that you are familiar with. It doesn't have to be something that you are currently doing in your project, but it could be something that you picked out of this course. It could also be something that you think you're familiar with. But the thing is, data should be easily accessible. Your data should probably be ready. It's something that it could be easy for you to have gotten the data. Maybe it could be from archive, it could be an archival data that you just need to collect, and then you now choose to know the kind of science that you want to do or the kind of analysis that you want to do. But again, anything that you're doing should be reproducible. Everything should be described in your Jupyter notebook. Your plots, your code for doing the analysis should be able to describe the problem that you want to do, what you are looking to achieve. Then you also provide the analytics, like the example codes that you have used to either clean the data, refine the data, make some plots, describe the plots that you have made, and then use that to describe any science that you've obtained with it, or analytics, the insights you have derived from doing this. So if you want to work on time series data, there's Kepler. You can also take instruments from data from maybe ground space telescope. Some may have been published. They might even be available on Visia for maybe any kind of star, any kind of galaxy. It could be AGN, and then you can pick them and know the kind of science that you want to do with it. And I don't know if I answered your question. I think we do not have enough time. We need to quickly jump into to the notebooks. So if you go to the GitHub repo for this course, you will see the notebooks. These notebooks have been published since last year, although there's a new one there. 04 was added. I added it this morning, but that is just for you to glance through to provide additional, more in depth. So time is something that I've described before. So time is something that we all work with, right? We humans, we work with time. In astronomy, we do the same thing. And times I usually also have referencing. So if you are what's it called? If you are describing to somebody, especially if you maybe discussing something, a project with someone, you can say, "Oh, can we meet so time?" Right? If you are living within the same place, if you are not living within the same place, if you are living in different time zones, you have to say, "Oh, you have to choose a reference time," like, "Oh, UTC." Those who live in America will say Eastern time. Some will say Central time, whatever, right? People in the UK will say GMT. People in West Africa will stay West African time. Those in South Africa will say South African time. Indians will say Indian Standard Time. So you can see how these things vary. Those are just references. So the concept of time have been described in this notebook. The first 101 time Python. I've tried to describe it and how to write the concept of time in Python. We have a package in Python called datetime. So datetime allows you to get the information about the time. Let me see if I can run this notebook. So if you see, I just run this notebook now. And with datetime, I said, get me the current moment. So the time, just right immediately I ran the notebook and was able to pick out the correct time, 2026, June 03, and the time. So this time is, I guess this time is in, oh, sorry, I'm not so sure why. So the time is my local time here, right? So the 9:46 is my local time. And then now you're able to split to get the year, the month, the day, the hour, and the minute. So imagine if you are somebody working on a project and you want to do some sort of analysis that has to do with time that you want to maybe referencing. So you can pass a time object into datetime and be able to get this information. So this is just the general concept of time. But then I'm not going to dwell on this because this is straightforward to understand. I would like to go more into the ones that relate more in astronomy. This is just for you to see that even without the concept of astronomy, you can do time-related stuff in Python. Here is another example that shows you how to represent time parameter as a table, right? As a pandas table, and how to fetch information from it, how to perform conversion, and the rest of them, and how to filter time and the rest. So please go through it and make sense of it. This is where you're setting time as an index, and then you have your values and the rest of them. So this is just an add-on notebook for you to make sense of what date time is and how to play around date and time in Python. But we're going to go more in depth into the time domain, right? So time domain in astrophysics is something that is very, very big. So time domain astronomy is the science of astronomy that has to do with time. So observations are done, every observation being taken are done in reference to time. And the reason why it is very, very useful is that astronomers do not always have all the time in the world, right? Telescopes also have limitations. Observations also have limitations because multiple people can be chasing time on a telescope, right? So, and there are some phenomena that are very, very interesting. Imagine, when a supernova outburst is going to happen, right? Wouldn't you want to see it? Wouldn't you want to get the data? Imagine our own sun is going to flare. There's going to be a coronal mass ejection. Wouldn't you want to know when such coronal mass ejection will happen? There are people who do that you don't do it. I'm just saying it in reference to astronomers or solar physicists. There are people who spend their time to do this because there's something to learn. There's something new to learn. Many of them may not have direct impact on Earth. Many, in the case of the sun, can, because each time I talk about time series or time domain, I know a lot of people always want to look at the stars and stuff, but we can talk about our own star, which is the sun. Many of you know that I've heard about the aurora lights, right? The beautiful light that you see that happens in the northern hemisphere, or people living close to the northern hemisphere like Finland, Norway, and the rest of them, or around Australia. Aurora borealis, aurora whatever, right? Those things are after effects of flaring happening in the sun or coronal mass ejection, where these hot plasmas move towards the Earth. So when they move towards the Earth, they interact with the Earth's magnetic field, which that tries to deflect them. And when it's deflecting them, you see those colorful lights. I think there was plenty of it last year, if I'm correct. And it happens at intervals. If many of us here living on the continent will not be able to see it because we are far from the poles. And I know a few people say they've seen it in South Africa, but I've not been able to see it myself, right? So there are multiple things that you can do with it. So time domain astronomy, from the optical point of view, is something that a lot of people have been chasing because it allows us to understand astronomical objects. It allows us to describe even the shape of a light curve, right? Understand us to say, okay, when you see certain shape of a light curve, you could tell the kind of object that this could be. They can tell, oh, maybe this is some sort of spectroscopic binary. This could be RSCVN. There are so many names for it. If you go to a Google variable star types, you're going to see different examples that's going to be listed on Wikipedia for you, or even websites like AAVSO. I think it's American Astronomical Variable Star Observatory Organization. So they also have some sort of plenty of blogs describing variable stars, right? Now, transients, on the other hand, are the ones that are not so frequent, but then they can be sudden, but they can be very, very bright. It is a case whereby maybe certain phenomena or events happen in a star that gives it a kind of bright. It could be a merger, and sometimes it could be like two stars. There's a coalition of stars. There's a merger. It could be a case of huge mass transfer happening between two stars that is moving within a common center, like in some cases binary stars. It could be a supernova, could be a gamma ray burst. So there are many. It could also be a pulsar for those who study pulsars, especially in the radio. Those who do radio astronomy, that study pulsars, where you can point a telescope and then you see some streak of lights coming from the source. So you have this sort of events, right? Yeah, but then how do you do them? So in astronomy, we do have popular telescopes that are being used for chasing transients or chasing variable studies in optical. Amongst them, very popular amongst them is Zwicky Transient Facility. It's I think it's a telescope based in the US, ZTF. And then it's within close to the northern hemisphere. It's been one useful telescope that has been observing the night sky and publishes tons of data. They have their brokers for how to query them. So brokers are like instruments. Some are like Python. Most of them are like APIs on how to query data, like search for maybe latest data that was observed in recent times, do some analytics that you want in respect to the kind of object that you're looking for. So ZTF has been the top of it. We also have here in South Africa, we have MeerLIT, which is part of it was originally designed to follow MeerKAT observations, right? So it was supposed to follow MeerKAT is the radio telescope here in South Africa, and then MeerLIT was supposed to be the optical counterpart that follows MeerKAT. So MeerLIT too has been gathering a lot of data for time domain data that a lot of people, if you want to do like multi-wavelength analysis, or you want to look at the optical photometry of the light curves, like you want to study them, you want to see some variational changes, you want to see something like the color index, right? These are some of the things that you can do. But then in recent times, we now have the LSST. The LSST was it's also a US project that started way back, but it also allows for international collaboration. It only started operation last year. In short, it is dominating when you're talking about transients. We're talking about time domain astronomy. LSST is the go-to. Although I'm not sure the data is. I'm not sure the data is publicly available yet, but they have in-house rules for those who are part of the collaboration on how to assess the observations that LSST have been taking so far. So far, it is the highest resolution, if I'm correct, camera ever made in astronomy, right? But now you now have other projects that are still ongoing. So you also have things like Gaia. While Gaia, is a space telescope, it's an European space mission. It also collected light curve data that is also publicly available on Visia if you want to analyze it. So yeah, and so the essence of time domain is to understand how objects behave, see how their light, their measurement, their fluxes change over time. But that is not enough. But then it allows you to see, it gives you room to describe. Somebody asked a question in the chat earlier, are light curves periodic? Oh no. If you have enough observations of a star or galaxy or whatever for a time, you can maybe after inspecting it say it is not, there's no period, you can probably not find any periodic event that happens in it. But there are some cases that you can find some sort of periodicity. It could be outburst, it could be flaring, it could be mass ejection and the rest of them, right? It could be wind emission for like massive stars. It could be wind emission, things like Wolf Rayet or will be massive stars. So there are a couple of things that you can do, but in programming language or in the programming paradigm, Python in particular, how do we do this? You were introduced to AstroPy last week, if I'm correct, and AstroPy is a suite of astronomical analytical tools. So AstroPy, just like NumPy for numerical analysis, numerical Python analysis, Matplotlib, Pandas for doing things like analyzing tables, doing filtering, cleaning. You also have AstroPy to do things that has to do with astronomy. Could be for loading astronomical data, which Priya and Alex showed last week. It could be for reading time in astronomy. Could also be for loading things like spectra. Could be for loading images. Could be for loading catalogs. Could be for filtering and many other things, but things that has to do more with astronomy. So we're going to look at a very simple example with respect to using time with AstroPy. So if you want to use the time framework in AstroPy, you have to say import astropy.time from astropy.time import time. So with that, it will allow you to, so let's do that now. And I've imported this. So I also imported other packages like NumPy, Matplotlib. Now you want to create an object. If you want to create an object, you pass the time object as a string, and then you also pass in the reference frame. Use scale to pass in the reference frame. So if you look at this observation time, UCT, when you run this, then you print it, it tells you, time from ISO string. So this was 2023, November 15, 12 p.m., right? UCT time. I don't know what happened that day. I'm not sure what motivated using the time, right? Right here. So, but then, remember I told you before, in astronomy, we have times to represent different reference frames. So the same way you have UTC, GMT, IST, WAT, we have time with respect to dates. These dates do represent certain things, like the Julian date. It says a continuous count of days since noon universal time of January 1st, 4713 BC. So this was before Christ. I'm not sure what motivated that, to be honest. I think I've read it before, but I can't remember how fair that, what motivated why they had to resort to start counting dates from that very day, right? Yeah. So, but I think there's a link that's also provided that you can read to get the details on what motivated the idea of a Julian date. I think there was probably an event or something that happened that day. So it has become the de facto way of representing time in astronomy. So you have the Julian date, but then at the same time, you now have what we might call other variations of the Julian date. Yes, I think there are cases where it was, oh, this number has become so long, let's see how we can shorten it. That is where things like modified Julian date and the rest of them happened. So you see this now, we want to convert this time that was created here to a Julian date. In short, I think I'm going to switch this to today. So this is 2026, and today is 06 03, and the time is just 10 o'clock. So let's just maybe play around our current time to see how these things are. So this is showing us today's dates and just around. So this is around my time. I don't know where you are, so I don't know what the differences are, but I'm using my just referencing close to my time. So Julian date, we want to convert this. So now we have this time. So this is a Julian date number, and then converting it to normal time is showing us that, let me see. So ops time to Julian date. Okay, just a moment. Oh, okay. So I think this is wrong. I don't know what the Julian date is today, but I think there's a way to convert the normal time to Julian date, but we'll see to that. We'll see to that. So if you want to have a date, there's a format here. So you have scale to show the reference frame, and then you have the format to say, I want this time is in Julian, this time is in Julian dates. Then you have the one for modified Julian dates, which is, it says modified Julian date is days since November 17, 1858. Common in astronomical archives. Yes, to be honest, a lot of dates these days are represented in MJD. It is shorter because the Julian date you can see is about 2 million plus days, 2 million plus days. But the modified Julian date is just between 69, is usually hovering around 60-something thousand. And then this is saying converting between dates. Let's see what happens here. Okay, so, oh, good. So you see, today's date is the 3rd of June, 2026, 10 a.m. This is the time in modified Julian dates. It says 61,190. We're in the 61,194th day of the modified Julian dates. And then we are in the 2,461,194th day of the Julian date. Yeah, so beautiful. This other things is more like performing arithmetics, like how many, like this is more like if you want to add another day, right? If you want to add another day to your current day, how to do that in astronomy. Like maybe you are doing some analysis, maybe you want to do like prediction. I think this is very useful if you supposedly you want to do prediction. Yeah, so you can see, I think this is the time, and this is our current date. So this is I think since November 2023 till now is about 930 days difference, and in hours is about 22,330 hours. So these are a couple. Remember, we're doing all of these things with the time package in astronomy, right? Then here we talk about light curve. So light curve is a two-dimensional data that represents the brightness, the observations that you've carried out with an astronomical instrument, say a telescope, and over time. So you can, it could be photometry, it could be spectroscopy. It could also be polarimetry, right? So polarimetry is when you are interested in finding things like the air fields, or what's the polarization. The concept of polarization is that you take an electromagnetic light and then you're able to split it to see the behavior of the electric field and the magnetic field. So usually in astronomy, you can have it as linear polarization and I think circular polarization. So, but that is not what we are talking about. What I'm saying is that irrespective of the kind of science that you want to do, you can still narrow it down to a light curve or a time series. There are also like spectroscopy in case of spectra, where people observe spectra and also give the information in record time. You can maybe things like over time do things like H-alpha analysis to see how the H-alpha emission or absorption differs over time, right? So usually light curve are represented in X and Y axis in a plot. The X axis is usually the time, and the Y-axis represents the measured property, be it magnitude, be it a flux, right? These are all described in this. So we're going to look at some example. So I think this should work. So we have an example of a light curve that we're going to query directly from VISIA. So VISIA catalog, VISIA, if you go to Google now, type VISIA Astro, Google will show you the link. You can open it and you will see there are tons of data sets there. So, but there's a Python API that you can use to query the same data from VISIA. So through AstroPy sub package called Astro Query. So if you do this, I'm not sure if, but we're going to check now. We're going to check now if this works. Good, it worked. So every data published on VISIA have a reference ID. So the reference ID, so in this case, JAJ166253 Fig 1. So I can actually search for this myself. Let me see if just tell me if you can see my screen. I think it's sharing. I'll do VISIA. VISIA this, VISIA is my track error. Good, okay. Yeah, so this is the VISIA. This is how it looks. I think this is the older one. Usually when you search on Go, it opens, it usually takes you to a final interface. So all I need to do is this place. If I paste this here, the ID, I think I already searched this myself and click find. Yeah, it tells me that this is light curve of the best fit parallax orbital lens model for Oakley. So Oakley is, I think this is a transient. I'm not sure what this object is. I think it's a transient. So you can see it has the heliocentric Julian date. It has the apparent magnitude and the error in the magnitude. So the I band is also is a filter, like, so it's optical. This is optical observations. So here we have queried this data already. Are you looking at this data? Looking at this data, it says it has about 5,018 rows. So with this, so a good example now, for those who have been talking about how to do, what's it called again, capstone projects, you need to think about things that you want to work on and quickly go to VISIA and search if you can find data related to it. You can simply just use this method and query the data in seconds. You see this, if you run this, it's not going to take you, see, not even up to 2 seconds to query the data. So this is just showing the first 5 rows. This is the instrument name KMT. This is the HJD. This is the heliocentric Julian date. This is the magnitude and the error in magnitude. Now, all you need to do is to plot the light curve. So this is the same plotting method that you have been using in your week 2, week 3, and I think even week 4. It's the same plotting method. There's nothing new. You just need to plot. Remember, for a light curve, the x-axis needs to be is the time, whereas the y-axis is the measurements itself. So let's do that, although you already said it. So this is the light curve of Ogle. So I think I should put the name of the I don't know if this is a star or what again. So there was a label here. Yeah. Good. Okay. So yeah, so this is heliocentric Julian date is actually Julian date minus 2,450,000. So you see heliocentric Julian makes even the numbers shorter. Just I think it's still hovering on, it's hovering around 8,000 something or 9,000, I'm not so sure. Right? So this is the magnitude. For those who might be confused, I'm not sure if you attended Priya's class, but the reason why you are seeing the numbers go in the lower in the y-axis, why the number is going while the number is lower up is because you are dealing with magnitudes. So in astronomy, magnitudes, the smaller the magnitude, the brighter the source is, right? So, but if you are dealing with fluxes, of course, it should use the normal, it should be the normal way for ordering. But for magnitude, you have to reverse it. And there is a function for it in Python. I just want to confirm if I can see it here. Not this. Yeah, invert. So you see here, let me zoom in there. So if you see here, invert. So this will automatically invert the y-axis. So let's play around. Let's say for some reasons, we didn't do that. You can see it's going to be inverse. You can see this is now, you see how it looks, right? Yeah, so when you are dealing with magnitude, please pay attention to this, just so you don't make mistakes. But if it's fluxes, you can leave it like this. But if it's magnitude, please make sure you invert it. So let me invert it back and put it so that, now you can see in this case, you see here, there is not a lot of variation in this observation from a little lower than 8,200 to 8,400. We can see that there was not much of a variation, right? Although there seems to be like something little, but the data point is very small here. Maybe if you zoom in, you might see maybe some small variability, right? But again, you can still not count it because it is everywhere. But then if you look here, you will see that there's a strong brightening. Are you seeing this? And then it drops again, and then there's another one that goes even brighter. So in this case, this is a very good transient, right? Maybe you can read up on the object again. I don't know the kind of transient, but I think most ugly, I don't know if it's a CV. It might probably be a cataclysmic variable, but I'm not so sure what it is. So now the point is that I'm trying to show you exactly what a light curve looks like. Now looking at this, it brightens and then it goes down. So some things that you can do, normally supposedly you are the one looking at this data for the first time. The question you might want to ask would be, how many times did you observe this sort of variable, strong variability? In my case, I would say 2 times. It brightened, and then it dropped, and then it brightened again. Now you see the duration of the first brightening is it's long, right? It was long, but you see in the second one, it just brightened and then fall off immediately. So you can begin to note these things down based on what you are observing with your eyes. The other question will now be how bright, right? When you say something brightens or flares, or varies. What is the order of magnitude? So in this case, if you barely looking at this light curve, you can see that the star's brightness is, the object's brightness is hovering around 19-ish, right? 19 magnitude, between 19.1, 19.2 magnitude. And where I'm referring to this line here, right? But then immediately, when it started brightening, you see that the brightening went as far as 18, almost 18. So you see from 19 to 18. So it means that this thing brightened by one order of magnitude. And then when it even got down, it even went more than 18, went to like close to 17 and a half. So 1.5 order of magnitude. So these are the kind of things that you might want to describe. But it all depends on the duration of the light curve that you are looking at, right? So that is one thing. Then here's another object. This is called, this is Sagittarius A. So this Sagittarius A, for some of you who deal on high energy objects or things related to black hole or galaxy studies, it is the black hole at the center of our galaxy. So there was a data, this data is also available on Visia. The paper, if you want to read the paper, I think the link is attached here. So if you open, let me see if the link for the other one, it wasn't attached here. But for you to find the paper itself, you can simply just take the, you can, yeah, okay, in the case of this ugly, for you to find the publication, all you just need to do is to click here. It will take you to NASA ADS, I think. Yes, it will take you to NASA ADS. So you can see, this was a data that has to do with, I say, discovery of a wide orbit Jupiter mass planet around a late type star, whatever. So if you want, you can go to the preprints. If you are within the an astronomy institute that have access to the journal paper, you can click here to read it. Otherwise, you can access it for free by clicking the preprint PDF. It will open Archive for you. Archive is free for anyone to read. Yeah, so let me go back. That is not what we are discussing this morning. I'm just trying to, for those that are interested in reading the paper, you can easily, quickly do that. Yeah, so this is the data for Sagittarius A. I think this is the Visia ID. I'm not sure how big this is. I don't know why it's taking time. Or it could also be my internet. I think it's my internet. It's not moving for some reasons. It looks a bit, because even the PDF here is not opening. I will see. So let me search for this. Let me also search here and see if it's a network problem. All right. It looks like I'm having, can you guys hear me?
Yes, we can hear you, sir.
Okay, so I think for some reasons the internet is not fast or something. Yeah, I see it is complaining. Yeah, it's complaining. So I'm not sure why. Okay, the paper opens now. Try for this one again. Okay, this one opens. So let me search again for one more time. Otherwise, if it doesn't work, you can run it by yourself, and I believe it should work. Oh, good. So I think it was the internet earlier. So now this is the data set for Sagittarius A. So this data is from Spitzer Space Telescope. So Spitzer is an infrared telescope, and it was used to observe the black hole at the center of our galaxy at 4.5 microns. So remember in the optical wavelength, it spans from around 3,600 to 8,000, I think 8,000 to 8,000 or so microns. Yeah, microns. No, not microns, in angstrom. So which can be called, you can say, okay, 300 to 800 microns, micrometer, right? But SPIXA is about, no, what am I? 0.3 to 0.8. So SPIXA is about 4.5 micron, right? So this is the data. In this case, it is represented as a flux, and the time is represented as modified Julian date. So if you're taking this data and you plot it, this is how it looks. So what can you say about this data? So you can see that the morphology of the light curve differs from the first one. In this case, we do have short flares here, right? You can see the flare was dimming, and then there was a quiescent mounted, and then you saw this, you notice these two flares, and then it gets into quiet mode again, and then it starts flaring, and then gets quiet again, and then even goes into strong outburst, comes back again, flare again, goes into another second outburst before it goes back to quiescent. So quiescent here refers to when the data is flat. So when I say quiescent, I mean that is, if you look at it, so that over time the data looks almost flat. But then flaring is when you see the lights, data points go up. So this is just for those who are maybe concerned about the terminology I'm using here. So you can see these are two different objects. The light curve differs, right? The morphology in the first one is different. There are a few things that look alike, like the outbursts, right? Probably almost similar duration. So that is just what I want you to get from this. Now, remember the first one was optical image, optical light curve. Second one is infrared. And then the third one is radio light curves. So I don't know how many of you work in radio astronomy. So radio astronomy data can be very, very tedious to get. But then people who work on AGNs, galaxies, you can maybe have like observations that can allow you to take like snapshots for like days or like intervals. You can say, oh, I want you to observe my target 2 hours every day or 1 hour every day for 1 week, or maybe once a week, continuously like that. So we have a case where I'm not sure, I think this data was collected with this J14. I'm not sure exactly the let me see. I'm trying to pull in the data. Okay, we've gotten the data. And then I think this is an AGN data. I'm not sure which instrument was used in collecting this data, but this is a normal flux, and the flux here should be, this flux is in Jansky. So let's check. So all of this data used here, you can easily access it here. You can search, and then you can see the table yourself. You can download it yourself. So this is Costello. You can read the paper. If you read the paper, you'll be able to get, I'm not sure what this radio source is all about. Yeah, so so I'm not sure the telescope that was used here. Here we report discovery with apertive of a source. Apertive, not sure what that. Okay, so that's not the major thing, but we also want to see how the light curves can also look in radio. So here, so but the most important thing is that this data was taken at 1.4 gigahertz, like around the same band with 21 cm. So you see in this case, yeah, it's very short light curve. But what can you see? You can see the flare. There's a flare all over the duration of the observation. Although as the observation progresses, the flare was increasing. You can see it here. It started here, then it kept increasing until the highest peak and all that. So this is what you can do in describing your light curve. Then questions can arise like, what could be the physics behind this sort of flare? That is when you begin to look at maybe literature, or what object are you looking at? Because you need to understand what is the physics behind events, what is the intrinsic events happening on this object that it makes it to like give off this kind of brightness variations, right? Is it short time? Is the brightness changes? Is it short? Is it short scale? Is it long scale? Right? Like in this case, you can see this is more like short scale variations, right? It brightens, goes down quickly, brightens again, goes down very quickly, brightens again, goes down very quickly. Like it's not as lengthy as this, right? But it's also important for you to scale your timing. Again, this is not well. So okay, this is for a day. I think this observation, I think it's for a day, maybe for a few hours. And then you could see this this sort of variation. Yeah, so but I think the data was also placed here for RLU, a variable star that is about close to 5,000 parsec away. The light curve was obtained from Assassin, which is one of the telescopes for observing, very, very, very good for observing variable stars, right? So let me see what they described. You can see the magnitude ranges. Here it tells you remember the minimum here means how the brightest 15.5. The max here is like the faintest, like almost 17 marks. So you can see that the magnitude it all varies for like about 1.5, right? Good. And then if you plot this, you will see not so interesting, but again, for things like Assassin, things like Atlas, or things like Meerlit, you also see cases where the light curve is not modulated like this, like it's not like very linear, like you always see gaps. The reason why you see such gaps is because the telescope is pointing to multiple objects, right? And there's also a case of night and day. So it might not be observing at a particular. So the gaps is when it is not looking at the target. So the gaps is when it is, if it's its first telescope, the gap is when it is not looking at the target, like it's observing another object. So that is the essence of this. So, but in this notebook, the essence of it is to just show you how light curves are produced, how to make a light curve. It looks very simple to make, but after making it, you can begin to think of the kind of science that you can do with it. So for those that want to do something around time series analysis, it's important that you know the kind of object that you want to do, this analysis on, and know whether read about it, like, oh, is it a flare star? Is it a binary system? What's the duration of the light curve? Where are you getting the data from? Is it optical wavelength? Is it radio wavelength? Do you want to make combination of, let's see, if you have both optical infrared, do you want to compare the light curves and see whether similar morphology exists for this star? Like, if you might look at the optical light curve, look at the infrared light curve and see whether there is similarity, right? Or whether there is discrepancy in the modulation, in the morphology. Or even if it's flaring, if you see the flare in the optical, can you see it in the radio? Can you see it in infrared? If there's UV, can you see it in your ultraviolet? If you're looking at X-ray, for those who work on X-ray astronomy, what can you tell us about the X-ray? What kind of energy is it emitting? The flux range, is it a soft X-ray or hard X-ray? So if you are able to see X-ray, is it does it have something to do with wind emission or coronal emission? What was it telling you about the energetics of the stellar atmosphere, right? So sorry, I'm biased here because I do more of stellar physics than extragalactic like galaxy. But I think it's also a similar thing also happens. I think because I think in the case of galaxies, you have AGNs, you also have the sort of corona emission, but I think you probably will see them in hard X-ray because they are very, very super energetic, right? Yeah. So Harrison, I see your hand, but I don't know if you should you can wait. Let's you can write down your question, and then let's dig in further into another example before we call it a day, because I say time is not so much on my side. So I think this notebook it's just for you to consume, but I need to go into this one because I think this is more detailed. So remember in my presentation, I talked about what did I talk about again? I talked about TESS. So TESS is a NASA telescope, right? That is very, very ideal for photometric analysis. It provides light curve information. And TESS can be accessed through many places. I think that they do have the archival information. Let me check. If you go to Google, and I think yeah, if you go to Google, then you will see, say something like so the Space Telescope Science Institute. I think MAST archive. Yeah, see. So yeah, I'm not sure what the MAST stands for again. It's Minkowski Archive for Space Telescopes. I think that's what it stands for. Yeah. So it allows you to. This is where you can search for TESS. I think they do have. This is where you can actually come read more. Let me put the link in the chat for those that are interested. I hope this message is sending to everyone. Good. So I just put the link in the chat so in case. So you can, it tells you about the telescope. It has been active since April 2018 to present. So it tells you capabilities, time series, photometry, imaging, and the rest of them. So it shows you the wavelength coverage here. Well, it's just within the optical. See, it blanks out in the other sites. So this is the information about the 2-year sky coverage. So this is just showing you like part of the sky it has observed. And then the colors now tell you how many days it has observed this region. You can see the red one here. It's like, that is where it has been domineering in terms of observations, right? You can go to the documentation and read more about it. I see this also like information around the telescope. So then the search tools is where you can use here to search the MAST portal. If you want the image cut out, if you want to do bulk download, I think Cloud Access allows you to use the Cloud Access allows you to use a computing environment. So if you do not have, if your computer is not so great, like to run big data analysis, and you are trying to do something that is huge, you can use the Cloud Access. I don't know if it's restricted. I don't know what are the criteria for assessing it, but I haven't myself, right? Because there's a Python API that I can use to collect it. So the idea is to see that there are websites that you can go to do this. But we're not going to focus more on this. The another thing I want to tell you is the light curve package itself. Light curve package. If you search for it on Google, you'll see the light curve dots, and then you will see all right, sorry. So they developed the Python package for getting the data from TESS, right? So the next hands-on will just be to go and see how to use this package. So in the notebook, so it does have a couple of quick stats here that you can use. to, like, you can follow up, you install PyCorv, you can query data, get your images. They have plenty tutorials that you can follow. So this is a good start for those that want to do some time series analysis. If you want to do time series analysis that is related to tests or in any particular star, all you need to go and check is whether that star has been observed with tests. So this is me giving you shortcuts. There are a couple of examples that you can follow: how to create periodogram, how to find peaks, measuring and moving the rotation period signal. So like I said, depending on the kind of thing that you want to do, exoplanet example, yeah, you see. So they have numerous examples. Just find an object that you want to work on and see if you have very good data in tests, and you can follow the examples to get something that could count as a capstone project for you. Anyway, so now let's talk about LightCurve is a Python package for querying data from MAST, most especially tests. I think text and Kepler data, because remember, Python has become the adopted programming language for the science community and astronomy, right? So I think astronomy is one of the fields that went deep into using Python. So what this has enabled is that every telescope observatory are now trying to optimize their data and API query or analytics towards Python, right? Because again, why? Python is open source, so there is no restriction on usage. So long as you prepare all of those things and make it so you can use any of the functionality that already exists and combine them into producing your own package or code that other people can use. Good. So I think the latest version of LightCurve is 2.6. So this tutorial, this is actually a tutorial that is openly available, I think so. So 3 science case examples here is Kepler 8b, which is for planetary transit, that shows you it's one of those stars that have a planetary transit around it. So it did have exoplanets around it. So this is just how to install if you are running this on a Jupyter notebook. You have to install this. If you are running it in your environment, you may have also installed, you need to also install the LightCurve package, Octopus and Autograd in your Python environment if you are running locally. I'm running locally. This notebook is on GitHub now. I pushed it to GitHub this morning. I will still make some few modifications. I think I might have to make some few modifications later and still push it, but I think where it is now is already much enough. So you can also, in case for those who already downloaded the notebooks before, if you go there this morning, you're going to see the 04 LightCurve IPyNB. So it's also there. So just like in every other examples that we've done, we install the LightCurve packages, install AstroPy, install NumPy, Pandas, and Matplotlib for plotting figure. So the Matplotlib inline allows us to the plots to figures to show in the notebook. So this is 2.6.0 version. So software development is usually continuous, right? Why? Because there's no package that exists on its own. So packages are always dependent on dependencies. Even Python itself continuously upgrade. I think the latest version now should be either Python 3.14 or 3.15. I can't remember. I just know it's between 3.14. So what it means is that a few things have changed. So because of it, software developers continuously make improvements in their code. And when they are done with it, they publish it newly with a version. So the 2.6.0 is the latest version of LightCurve. Good. So what can you do with LightCurve package? Like I said before, LightCurve package allows you to query data related to Kepler or relating to tests on from the archive. So from this archive you're looking at here that I mentioned earlier, the one I showed you from NASA MAST, you, instead of going there to go and search manually from the UI, can be very, very tedious, right? And then searching, you look through things, you start downloading the one that you think might be relevant. Instead of doing all that, you can just create a notebook and then you run these things yourself. So looking at it, you can query the image. What we call target pixel files are just the pixel images that come from TESS. And TESS releases data per quarter or sector. So I'm not sure, I think if you go back to the documentation, you will see that. Let me see if I can do that now. Let's see this. Sector releases. Let me see if there's something like that. Okay, there's release notes. So you can see the sectors here. So these are the sectors, and I'm not sure. I think the latest one. Oh, the latest one is sector 99. That is the latest sector. But this is not the type. This is not the exact one I'm looking for. But I think you can. I think the PDF should tell you. Should be able to tell the information about the release date. Not sure if I can find it here. So this was April 13, 2026. So I think this is the latest, yeah, I think April, just less than 2 months ago or close to 2 months ago was the latest release date, right? You can read about it because data are usually available for sectors. So if you do those searches, you can find that. But then we want to query the Kepler 8 Kepler 8, what's it called again? Kepler 8 image. So usually if there's no, so remember in astronomy, we have names for objects. So usually IAU, the International Astronomy Union, have designated names for objects, right? So if a name have been indexed in the IAU, you can search for it and you can use that using that name. You can easily search for it and find the object even on archives. So in this case, Kepler 8 is a known object. How do we know that? You can go to something like Simbad. Let's see, Simbad will tell us. Let's search it on Simbad and see if so it tells us that Kepler 8 is a star, and it shows you the number of names. So these are other identifier names for it. So this is some of the things that you can play around with. 2 mass, it means observed by 2 mass. It was also observed by TESS, TIC. We have Gaia DR3, so it has also been observed by Gaia. LAMOST is, I think LAMOST is the Chinese spectroscopic telescope. I'm not sure what SPOCS stands for. I'm not gonna lie to you in that case. So there are, but I think if you click it, it will tell you what the name represents. Now, publications for this object, as at today, there are about 123 publications that have been made related to this very object. So you can click display and it will display. I'm not sure any of you know about, I think it's part of what Priyas discussed last week. So Simbad is huge resource. It's also part of the Vizia. For example, you see Vizia here, you see Aladdin. So Aladdin is the image. We can open Aladdin. So we use the Aladdin light. I'm not sure why it's taking me here. Okay, good. So this is Aladdin. So if you want to view the image, search and see. It takes us here. So this is the image of this star. I think, I'm not sure. I think this is currently showing me DSS. I think this is currently showing me DSS. So if you zoom in, this is the star itself. So this star happens to have an exoplanet around it. You can toggle among different telescopes. This is DSS-2. This is, I think it's actually in DSS-2. DSS-2 blue. Pan stars. Let's see if there's anything on pan stars. So this is how the pan stars look like. VTSS, I'm not sure, I doubt. So where this is a two-mass, so this is the two-mass object. Yeah, so is there a Spitzer? Let's see. I'm not sure because Spitzer mostly did things around the galactic plane. All-wise, yeah, there's all-wise, although the all-wise looks faint. So guys, this is just let's see if there's an eROSITA image for this field. No, it is not within eROSITA. What about XMM? This is for X-ray. So nothing in X-ray, nothing for Chandra in the field. Okay, beautiful. Let's go back to our light curve. So we want to get the image of this EPLA8. So we want to get the image for quarter 10. And you see, it doesn't take any time. You get your image and you have it. So it shows you the pixelations. I'm not sure the size of this field again. It's usually 10 to 20 pixels. 1, 2, 3, 4, 5, 6, 7. So this is 7 by 1, 2, 3, 4, 5, 7 by 6 pixels for this image for quarter 10. And then each of the pixels, you have the flux counts, right? The flux, these are, so here is called electron per second. So number of electrons in each pixel. This is the center of this is more like the PSF area, the center of the object. You can see the counts here are high at around 8,000-ish. Then this side is a bit hovering around 6 to say 3,000. And these edges are not, are more like background noise, right? So this is how you tell if you're looking at the color bar. So you can see how easy it is to, test images are not like other astronomy images. They are not like these ones you're seeing here. They are not like DSS images. Sorry about that. They look horrible. They are not as fancy. I don't know if they have a package to, I don't know if they have a way to do that, but I've never bothered to do more further work on that because I know I don't need to use Tesla's image to do that. I just need to see, okay, how does so the essence of just doing this is to see how the measurements look within the field. So this is the center. You can see it's strong at the center. In some cases, if you query and it's towards the edge, you know the data is not really good, right? Now, that is it. If you want to get the light curve data, you will have to, let's see, just want to try something now. Doing this my break. Good. So if you want to get the light curve, you use the search light curve function. If you want to get the pixel images, you use the search taxel pixel file, and then you pass the name of the IAU name of the object and the quarter. The same thing for the light curve. You can see it quickly fetches the light curve for you. Now, the question will be, and then so light curve also comes with plotting features embedded into it. So just calling the light curve.plot will plot the light curve for you, right? And then, yeah. So the question now will be, so let's do this. Let me see if I can play around this. I want you to see the table of the light curve. I believe you all can see the table. So it tells you that this is a Kepler light curve. Tells you the number of rows in the table. This is about 43, close to 44,000. Gives you the KIC number. I'm not sure what KIC, Kepler ID, I'm not sure what the C stands for. Quarter 10, upper Kepler flux origin, right? So it shows you all of this. You see the time. And the time is usually represented as barycentric KJD. I'm not sure what the KJD stands for again, or is it kilo something something? Then you have the fluxes in electron per seconds, the flux errors. The quality is 0, 0, 0. So I think whenever you see these huge numbers, this might probably be like outlier, but I'm not so sure. This is the information about it because they already done the barycentric time correction. So they provide the values for the time correction. The centroid pixel values and centroid row and all that. So I think this information here relates to the information on the taxa pixel file. Then you have the SAP flux and the background. You have the PDC SAP flux. So originally when test started operation, there were issues that had to do with the fluxes. And if you notice this, you see there's let me see if you compare this and this, you notice there's a slight difference in the flux in SAP flux. So these are the things you read in the light curve documentation. But these days, I think it's no longer much of a problem because I feel the flux information here they now provide is actually the same thing as the I think as the PDC SAP flux, which is the ideal flux that you need. So these days it's no longer what is initially before. You have to do a couple of corrections. It's mentioned in the light curve documentation package if you go to the documentation. So what we are interested in is just or maybe let's say these three values, the first three columns. If you look at this plot, you see the time is already plotted here, right? And then you see the fluxes. So the 24584384833 is the Julian dates. So it's reference to this, so that you can easily just read the date. So 910 to 935. Now, what can you say about this light curve? You see, looking at this light curve, the light curve looks quite nice. Looks interesting for many reasons. One is you can pick up flares. You can see starting from the origination here in this quarter, you could see a flare, and then you can see a dip. You notice that this dip. So for somebody who asks whether periodicity, so you can see there's a morphology here, this dip. This is a planet transit dip. You can see it here. This is periodic. This is why I think this is basically the reason why this is how they discovered that the star hosts a planet around it. Because over time, you notice that the light will dip sharply because it takes a very short time for the planet to go around to come in the surface of the star. Remember, you are pointing at your telescope is looking at a particular surface of the portion of the star. So if the planet happens to hover around the front of it, it dims the light. So you can see it dips sharply, and then it gets back to normal again, it dims again. So you can see it is constant. Like you can even tell that this happens for, I'm not sure, maybe close to every 4 days or so. You can tell this is how, or 3 point something days. I'm not sure if I have that information offhand. Yeah. And then you see strong flares too. You see these are very strong flare, this is a strong flare, this is a strong flare. Beautiful. So again, don't expect that all stars light curve will be like this. Some will be finer than this, some will be horrible. So it all depends on the star that you're looking at. Okay, so this is just us looking at the light curve itself. We'll describe what the light curves represent. If you want to get the PDC SAP flux, although we no longer need to do this because the flux that we have is basically what we're interested in. So in the past, it used to be an issue because you always want to use the PDC SAP flux, which is like the corrected flux. So it's a flux that they have been corrected to get rid of some instrument noise, desk instruments or artifacts or the rest of them. Although it doesn't necessarily happen, and sometimes even when you do all that, you will still see some artifacts information that you may have to find a way to get rid of in the light curve. So we've talked about two things now that you can do. You can get the target pixel file, you can get the light curve data for a quarter. These other ones are just you getting basic information like at what time was this thing observed, time information. It shows it to you in barycentric Julian dates. You can convert it to AstroPy time, although it's the same thing. Those are not, this is just saying the number of fluxes and the shape. This is sweep plotting, don't need to do all that. This is you checking for a max. So the max, I think, kind of like shows you. So in the target pixel file, it helps you map the pixels that was used in computing your observation. Like you can see in this case, they used informations around so these are the pixels that was used in obtaining the light curve information, not because all of these ones are noises. Right. So which other thing again? Something important that I want to highlight, these are basically the same thing. I'm not sure why I had to do this. Hold on. Okay. Yeah, this was not defined. So it's actually defined. I'm not sure why. Let me again. Oh yeah. So okay, this is just more like showing error bar. Let's see. Why? Let's do some plots. So here is just adding some annotations. We want to plot the light curve. We want to add some lines. We want to add some color. We want to, yeah, so that's just basically it here. So the data points are represented as using dash and red. So you can see the red dips very well. The 1, 2, 3, 4. So the peaks, that is the what's it called again? The data point that go above the or below the flat, the noise area, the quiescent region are all highlighted. So yeah, but then this is not what I want to dwell much on. Let's see. So this is just you changing if you want to change color, how you can remove outliers and then plot and change the color to red. You can do that here. This feature is no longer obtainable in the sense that you want to flattening. This light curve is nice, so we don't need to flatten it, but this feature might be useful if you have a weird light curve that you want to flatten. Not sure why we did this here. So you see the light curve here is being by 100 points. So you can see the quiescent area. You can see how there's more like a fit. Although this is not necessarily, this is not a fit, but it helps you to see the flow, the center point of the and shape of the light curve. You can also zoom in. Then let's talk about folding. I think the period for this star is about 3.5. Yeah, the transit dip here, if you look at it, if you count this is just a little above 9-10 days. Remember, this is 9-15, so this is 9-14. So the period of this star is actually about 3.52. Let's see. Let's use that information to fold it. And then when you fold it, you obtain your folded light curve, and then you get the phase information, and then you plot. Let's see. So now so this is what I'm talking about. Because in light curves, there are strong, actually there are features that are always there. Some can be micros, like can be very small, some can be minor. So if it's a case where it is periodic, immediately you get the period and you fold the light curve. That you will now be able to fold the light curve such that it reproduces that feature for you. So you can see the dips that we have been seeing here. Now, you'll be able to like find the period of this star, and then using that information to fold it and then create a phase. Now you can now see the shape very, very clearly. So it kind of like folds all of the light curve into one. And then you can see the dip very, very clearly. So this is basically the feature that was observed in this star that confirmed that it is there's a transit. There is a transit happening around it, and this transit could be as a result of an exoplanet, right? So, but this is for those who are interested in exoplanets. Not sure. I want to quickly run because I see we're already out of time. These other things here are not so, just some things you can play around with. This is a description of if you want to search, how you should search. Nowadays, please, I think this is search light curve, not just search. No longer search, because they've been updating the documentation. So search light curve itself, and then target pixel file. So, but then we search based on a quarter. You can search, usually you can do a blind search. Let's look for this one that is Kepler 10. You can do a blind search, and a blind search will provide all the information about that star that have been observed with Kepler. The years it was observed, the exposure time. As you can see here, this might take some time, but I think I ran this yesterday. Yeah, it's done running. So it tells us that there are about 109 cases where this star have been observed by Kepler and TESS, right? And the author, the years, the quarter for Kepler, it is quarter. For TESS, it is sector. So you can see sector 14 to 1526 has been observed with TESS. And then you can also see the exposure time. There were cases with Kepler where it was 60 seconds, 1,800, 1,800, and 120 for TESS. So now looking at this, if you're interested in say, oh, you want to get data for Q3, you can come here, put the name again and indicate quarter, and then it's going to download the data for Q3. And that is what it has done here. And then here in the Q3, it also shows you information about the exposure times, how many number of data it has. In this case, it has about 5. Right, it has about 5. 1, 2, 3, 4, 5. The exposure times are not exactly the same. 3 are within 60, 1 is 1,800, 1 is 1,765. Although I'm not so sure why K bonus BKG. I'm not sure, maybe there might be a problem with the data there. So anyway, there are all of these things. If you go to the Kepler light curve example, they are going to see all of these informations there. So this is just for you to play around to get all of this information. as you wish. So you can also search using coordinates. So coordinates like right ascension and declination. So you can search with using the name, IAU name of the star. You can also search using the coordinates name, right? You can also pass in the coordinates name using AstroPi units, and it will get the information for you, right? So there are many ways you can search. You can see here it's running. It's done querying, searching the coordinates, and it has downloaded all the data points. Yeah, so you can also search within a radius. If you know the name of the star you want, objects you want to pick, you want to search for, you can also pass a radius to it. Now, in this case, if you watched or if you joined Priya on last week, Wednesday, when she was presenting, she talked about clusters. So there are people who study star clusters, like stellar clusters. So you're not looking at one object, you're looking at multiple objects. So if you know within the region of the sky, that is very popular. You want to search for objects around it. So you can also use the radius to do that. In that case, it's going to query large chunk of data, and then you can start playing with the number of data. In this case, limit 3. You can leave it, you can probably remove the limit, and it's going to, if there are 100 objects there, it's going to provide the 100. Then you can start slicing or filtering for the ones that you're interested in. So let's quickly run. I think I want to get to, I want to get to periodogram. So to quickly do periodogram, so remember before I said, when you have a light curve, you can do period analysis. And you can do period analysis. And the period analysis are very essential because they avail you the opportunity to be able to find the orbital period, the rotation period of the object, more like rotation period of the object itself from the light curve. But that is if the data is enough. It is not in every occasion that you're able to get very good periods. If your data is too noisy or there is no clear shape or variability in the light curve, you will not be able to get short. Well, period analysis is one field, one area in astronomy that can sound, looks like it's very simple, but at the same time it's very, very complex because there are so many intuitions, there are so many assumptions that you have to make about an object. So using light curve, you can simply just do periodogram. Just do periodogram, and then it does it for you. And then you can plot, right? And usually, for those who do period analysis, I think in this third notebook, there was you can see in this case, it was so nice. The object, this one has a very good period. From the light curve, you could see very nice periodogram. Just to the pick one here allows you to now calculate the day, right? So you need to run the third time series notebook. In this case, it looks very wet, but the reason why I had to choose this because I just want to emphasize that in some cases you might struggle with getting the period. So the strongest peak here happens to look like is this one. Let's see, P period at max power is showing us that it is about 1.17. So it's actually this one. Because remember, this is in frequency, this is power. So just about 1.2 days. Then let's fold. So yeah, so when you fold, it does give you the same thing that we had earlier before, right? It shows you this is the transit period actually for the exoplanets. It's able to show it to you. Sorry for what was there before, that was a different object. We also have the box least squares periodogram method, which also follows the Fourier transform, but this is slightly a different algorithm for doing period analysis, right? let's see what this will do for us. Not sure. Yeah, so if you use the periodogram itself, it just uses the Lomscargo. And here you can use the box least square method and then passing the duration, and it will also help you with the peak. So you see, using this method, the periodogram is different. I think I like this one. To be honest, I think I like this. Yeah, let's see what the fold looks like. Good. This fold's better. This looks nicer. So in period analysis, there are multiple concepts. Sometimes if you try fitting, getting your period with Lomscargo, you're going to fail. You may also have to try the box least squares. But please do more reading on this. There are a couple of packages. I've forgotten the name. I think it should be in one of these resources. Yeah, it should be. I think I did list them here before, so you can read on Lomscargo periodogram. The AstroPy have a very long documentation on this. But I'm trying to remember. There's another package that's commonly used. Just let me see if I can find this. I can send it in the chat. It's my goodness, why am I forgetting his name? Okay, when I remember it, I will when I remember it, I will share. But I'm almost rounding up, so not sure about Tyler. Not sure why it is not here. Not sure why it is not here. It's old these days. It's not really used like that, but a few people, it's also a Python package. But then it's not. I will recommend Typony for those that want to do flare analysis. I will recommend Typony if you want to do flare analysis, like you want to measure the number of flares that exist in your data points. You want to measure the flare duration. You can do that. Here we also have an example of querying AMU-MIC, which is an MDWF that is also very, very strong. And you see the light curve. So like I told you, light curves can be very, very weird. You see in this case, I think, don't mind, this is the light curve for AU microscopy. The flares, you can see the flares here. Although you can see there are like strong morphology in terms of the modulation of the light curves. There are these strong peaks and the minor peaks. I think many of them has to do with star spots, sorry, but then the flares are coming out very clearly. In this case, this is a flare, this is a flare, this is a flare, this is a flare, this is a flare. You can see in this case, there were cases where the flares were like periodic, right? Yeah, but the strengths are not exactly the same. You can see here, it becomes very, very strong here. This code example shows how to do some flare analysis to this night curve is very wide, so you have to detrend it, like flatten it a bit, and then so the flare will come out, and then it also highlights where the flares are in the light curves. Find the peaks where the flares are in the light curve. So these are a couple of things that one can do. You can do some characterization on the equivalent duration. So equivalent duration is the although this light curve is the time is very long, but you can zoom in. If you zoom in, you will see that the flare is not so sharp. It lasts for a period of time. So these are some of the things that you can also investigate about. But you read more about this in Typony. She's an astrophysicist. I think she did her PhD on flare analysis, and she developed a package called is it Typony or something? That's what it's called. Yeah, so tutorials for a detailed flare study for those that are interested in flare star. So I think we are done. But these other plots are just showing you the flares, number of flare amplitude duration, the flare duration itself, the peak amplitudes, and the equivalent duration, and all that. So, but anyway, I think I will stop here. And I see there are a couple of questions. Let me. Okay. Oh, recording stopped, but I believe the meeting is still streaming live on YouTube. Yeah, so I'm not sure where. Okay, I shared the link earlier. Okay, so my goodness, how was it? Can you please share one link as well? I'm not sure the link you are referring to. Oh, the Aladdin. Okay, Aladdin. So Aladdin is just, if you Google Aladdin Lights, there's also a software called Aladdin. Let me see if there's something I can find from here. And if you go to the so if you come here, you will see Aladdin Desktop. So if you click Aladdin Desktop, you can download Aladdin for your software. But Aladdin Lite is the version that allows you to open it live on a browser, and you can quickly search for anything that you're interested in. Okay, I'm not sure what again I'm missing. I'm not seeing it. To be honest, I'm not seeing a lot of questions here. Is this any way related to Fourier analysis? Oh yes, of course. So the concept of period analysis is basically it's a Fourier problem. So the Lumskargel periodogram methodology it's a modified version of Fourier analysis that allows you to handle data set with huge gaps. So usually in astronomy, because remember, like I said, it is difficult to keep track of observations for a very long time. There could be logistic problems, like maybe instrument is problematic, or it's observing another object. So that time, or it's like in the case of optical, it's during the day, so you cannot observe during the day. So there's usually gaps in data. So in cases like that, Lumskargel, it's I think it's a statistician that device. He's not He's not actually like a. I'm not sure it's actually an astronomer, but this method is like very convenient for performing Fourier analysis for cases where there's gaps, like time gaps in your observation. So it's still able to handle the data and find periodicity in it. Could find strong periods and also minor periods, like in stars. Those who do CV, you have the orbital period, you have the spin period, and there's another period. So like in the case of a white dwarf and a star, so the stars are also spinning by itself, and then there's also a rotation. So you need to account for those periods. So Lumskargel avails one the opportunity to find those periods. Yeah, long-term period and short-term periods. Yeah, so I want to know if we must include everything from week 1 in our capstone. So I don't know why, I've always said this before. Let me open the GitHub repo and see if I can find it. Okay, so I believe you all can see my screen. So if you come here, you will see the project. If you go to project, you go to capstone. So you will see the information have been described on how you need to present your capstone project. Title, data description, data cleaning. So just take things that are relevant for the analysis that you want to do, right? If you put the data from online, you can probably just put the link and download the data. Or if you pick the data somewhere else that is not openly online, you can at least show us how you rate the data, how you analyze the data, do some visualizations, perform some statistical analysis, exploratory data analysis, do some modeling analysis, interpret your results, conclusion, and put references and where you got your data from. So yeah, so but you can start now to start working on it. And data sources have been mentioned, most especially in astronomy. Like now I mentioned tests. If you want to deal with light curve, maybe you're looking at different population of, say you want to look at maybe stars, maybe you're interested in flare stars, you want to see if your light curve variability look alike or whatever, or if you can figure out how to measure the flares for the star, for maybe if you have all the data points since there's started happening, you can measure them together and see if you can actually count how many times these objects are flaring and the flare period. This is me just because we're talking about light curve today. Could be maybe you're looking at maybe other form of morphology, could be you doing period analysis. What kind of period analysis do you want to do? So I think that is what I would suggest that you do. Then if you want to work strictly on astronomy, you can explore any of these their data points, data sources. If you have other interests, you can go to Kaggle, you can go to, the links are there. Any of these links, you click it, it takes you there. You can also check for other places. You are not restricted to this. That is why it says suggested data sources. You are not restricted to these data sources. And how this thing will be graded is already listed here, right? So you know, this is the rubric. This is how your this thing will be. So you already have this information. Please just come to the repo, click project. You'll see Capstone. It opens and then you see it. And everything must be in a Colab notebook. The reason for Colab is you don't have to worry about uploads. And the person who's going to review it will not have to start downloading it to their PC. They just need to click the link they want to run. They can also run it on Colab free and see your analysis and the rest. Yeah, so I'm not sure if I answered that question. I don't know if there's any other question. I'm not sure what you mean by you find it hard to understand and how to start and what to include. I'll first ask you, what are your interests in this course? If you know what you are passionate about, what kind of research are you into? Or if you are a student that is just starting, you don't know nothing about research, can you think of something that you think you like in astronomy that you think you want to do? And maybe search for data around it. Yeah. Everything has to be in the notebook, please. So for example, you see how this notebook is. You see this notebook is detailed. So it contains text. So it contains text. So notebook allows you to write text. You can format them. You can use ##* to format the writings. So you can see there's a markdown, there is a code. So you can use markdown to write the text and format them the way it will look like, and then the code will show the code itself. And you run it, one can see this thing that you write there, right? So so that is the point of why we want you to restrict to notebook. Again, for easy sharing, because if you are doing reports, you might probably want to do it in something like PDF, and you may want to upload, and it now demands that people have to start downloading one after the other. But again, I remember in the second week, somebody asked a question around this. I say, you can write your own reports, right? Even the process of doing this in a notebook, prepare it as a report, but everything should be in the notebook. You can also add equations. If you think any formula will help one understand what you're doing, there's a way to add formula in a notebook. I think I had something like that earlier. I'm not sure again why it disappeared. Yeah, you can see this is an example of an equation. You see how this equation was added. You can ask ChatGPT or any of the AI to put the equations for you in LaTeX format if you don't know how to use LaTeX. That you want to add it in a markdown and it will prepare it for you. You copy it and paste it and it will display it properly for you, right? If maybe that is a problem, because I know some of you are like students who are just starting, so you know nothing about LaTeX and all that. Yeah, so that's it. Deadline for submission, please, no more than 2 weeks after end of course. So after week 8, you are given 2 weeks, so you should start now. So you need to have an idea of what you need to work on, start collecting your data, use the examples, and other things, information that you know. You must not restrict yourself only to the analysis that have been taught here. You can explore other things to show that, oh, you understand the concept of what is being taught, the concept of what Python is. You have a problem. How do you solve the problem? Right? What is the analytical way of solving the problem? So just like, for example, if you are learning Excel, somebody taught you Excel. The next thing will be, after teaching you how to perform, say, statistical analysis, you will have to find your own data, plug it into Excel. Then you have to use the Excel tools and functions to perform, do some arithmetic calculations, do some statistical analysis, do some plottings and visualization. So that is what we expect you to do as well. But this time around, you need to do it with Python, right? And be able to interpret what you have learned in the course in the project that you are working on. This is your own, you own it, right? So don't expect that when you bring a topic, I will understand it. No, I wouldn't understand it because I don't know everything. So it should be something that you like. So while you're working on it, you should explain it so that someone else who is reading it will be impressed, right? You can write a blog about it. A couple of people last year, they were sharing whatever thing they are learning on LinkedIn, on their other social media platforms, right? There's also something called learning in public where you can share. So you can write your own blog to explain that you did this, took this course, you worked on a project, notebook of what you worked on, describe things that you think you might not want to put in the notebook, because we expect you to go detailed in the notebook. But if it's too scientific and you are just sharing it in the public, you might want to also simplify it, like use some easy words that people can understand. So I think we've gone off time. We've gone 30 minutes into the time, so I need to end now. So I think we'll stop here. We'll convene in the evening for those who, I'm saying how many references should we include? Include as many references as possible, at least minimum of 5, right? Minimum of 5. Good as many as possible. Yeah. So that's it. I think I will stop here, and no other assignments. Pay more attention to these other assignments are just regular thing for you to do, but the project itself is what will demonstrate that you understand the essence of this course that you're taking, right? So the capstone project is what you should pay more attention to, because it's going to be very, very relevant for you moving forward. It's also something that you can share to a researcher. Some of you are just starting. You can say, oh, I already know how to learn. If you say you know Python programming, nobody will believe you. But if you show that, oh, this is a project I did with a notebook, most astronomers, most of their project, they do it on notebook. They'll be like, oh, wow, you're able to do this, right? So some of you are looking for scholarships, some of you are looking for opportunities, maybe to do your master's or to do your PhD. So this is how you prepare yourself for people to see that you can actually code in Python and you can use the programming language to solve problems of do scientific analysis. So we'll stop here. Thank you very much for joining us this morning. Please, we'll reconvene again in the evening. It's not a must that you join. The evening is for those, I believe, those who were not able to make it this morning, or those who, those who were not able to make it this morning, particularly those in the Western Hemisphere. So thank you very much. Do enjoy the rest of your day. And please take more time to follow the notebook and read slowly. practice intermittently until understand the topic. Thank you and do have a nice day.